Are you guys doing okay with lab? Oh, I haven't projected this yet. Are you guys doing okay with lab 2? Has anybody tried that yet? Or you are yet to do that? I recommend if you haven't done so already, please start working on it. Always start with some margin because I know that there is this um, late penalty waiver available to you, but before you know it, you'll see you'll be ending up using all of this available waivers. Right? That's how we are as human beings. Like we feel like, oh, you have an option, sure, let's use it. But then before you know it, you'll see that you have used up all three. Anyways, and if you have questions, if you face any issues, please let me know. All right. Uh, okay, so today we will start a brand new lecture, and we are kind of diving into the core components of logic design in general. So the first few lectures was kind of universal in a way that, so for example, when you learn K-map, it doesn't just apply to one kind of logic gate. It applies to anything, any kind of random logic, the random Boolean logic that you can come up with. But gradually, now that we have this baseline set, we will dive into some key components that you will be using, if you stay in this domain, throughout your career, you'll be using almost forever, right? These are like universal building blocks of digital logic. So we will learn about some of them today. Multiplexer, decoder, and encoder. If you remember, we had a very quick discussion about multiplexers with adders, right? I decided to just take it out way before its actual place because you had a lab to work with. So I wanted to just give you a perspective. So hopefully it will be a quick lecture on multiplexer. I hope you guys all remember your lab 1 activities, right? You worked on multiplexers. So, but still, we have some additional information versus what we must have seen in the last lecture on multiplexer. So a multiplexer, what it does is it takes a bunch of inputs and it connects that to the output selectively. So for example, if you have a 4 to 1 mux, 4 to 1 mux, it basically takes 4 inputs and connects to one output, right? And to select between these 4 inputs, you need 2 bits of control. Because 2 bits will give you 4 combinations, 0, 0, 0, 1, 1, 0, 1, 1. Now, if you need 8 inputs, if you need to handle 8 inputs, you'll need 3 bits of select signal, and so on. Now, for some reason, if you need, say, 7 input rows, you still need 3 bits because there is no way for you to have anything between 2 and 3 bits, right? So that's it. You leave one of the combinations unused. So that's okay. Now, there are ways to just keep using the same mux, say 4 to 1, to make bigger ones. You can use multiple 4 to 1 mux to make 8 to 1 or 16 to 1 mux, or you could design a mux which is itself 8 to 1. For example, this is an example of an 8 to 1 mux. So these are all block diagrams, so you don't see the difference, but when we actually go and implement the circuit, you'll see how that changes. All right, and hope with the ideas that we have gone through so far about multi-stage circuits and multi-input circuits, you will hopefully appreciate the difference between the two. Like in terms of Boolean logic, they're basically the same. If you implement 8 to 1 mux operation with 2 4 to 1 mux, should be in terms of functionality the same as 8 to 1 implemented directly. But in terms of hardware performance, it will definitely be different. All right. Now, I want to show you how to come up with a functional output or functional representation of any random mux signal, 4 to 1, 8 to 1, 16 to 1, you name it. And it's basically fairly easy. Let me show you. This I0 to I7, they represent the input. That's why I, right? So you have 8 inputs here. Now, this is my select combination. So if you remember, if I have 0, 0, 0, I should consider this input taken to the output. For 0, 0, 1, the second input should go to the output, and so on, right? For 111, the final input should go to the output. That's how this thing is set. Now, keeping that in mind, remember my variables are ABC. So what is the functional expression corresponding to 0, 0, 0. We have done this many times. Can I write A prime, B prime, C prime? Right? So when A prime, B prime, C prime occurs, you select I0. Or 0, 0, 1. I could use A prime, B prime, C to represent 0, 0, 1. When this combination occurs, you select I1. When 0, 1, 0 occurs, that means A prime, B, C prime occurs, you select I2, and so on. Do you see that, folks? As simple as that. Or alternatively, you could always create a truth table and have this combination 0, 0, 0, 0, 0, 1, blah, blah, blah. And the output could be set to 1 depending on which input you want to send to the output. And then you can use any of the methods to do so. Or you could do is just using simple logic practically. So do you have any confusion regarding the functional expressions for mux? Isn't that very straightforward? Are you confused or no? Okay, so it looks okay to me, I think. And just give it a thought. Try to come up with these expressions yourself without looking at what is there in the slide, logically, and then check whether it matches with what you have in the slide. Okay, moving to the next slide. Now that you have this 8 input mux, how can we represent that in actual Boolean hardware? One easy approach would be to take each one of them. So this is essentially an AND gate with how many inputs? 4. 1, 2, 3, 4. So you have this 4 input AND gate, another 4 input AND gate. So similar to what you have done before, you have all these AND gates, and finally you connect them as an OR gate here. Haven't we seen this many times? So by now we should be pro at this. Okay, so this is a 2-stage implementation like we typically do. However, based on our discussion in the last couple of lectures, I hope you know that if you have more, okay, what is the fan-in for this OR gate? What is the fan-in, folks? Can you count? This could be an interesting quiz question as a MCQ, right? It's a very easy MCQ. Yes. Yes, thank you. Yes. So just count the number of input. 1, 2, 3, 4, 5, 6, 7, 8. So all these 8 inputs are coming into the OR gate. That's its fan-in, 8. Did I tell you that the more the fan-in is, the slower the transitions will be eventually? And there could be other challenges, of course. So you don't which I haven't discussed because it's completely beyond the scope of the course. But you don't just randomly have really high fan-in. And if you want to get a number in your mind, typically fan-in beyond 4 is challenging to handle. Okay, just keep that in mind. 4 is kind of like the sweet spot. Anything less than that, I mean, it's probably an overkill. Anything more than 4 will lead to performance degradation. So it's kind of like an optimization problem. It cannot be too high or too low. So 4 is typically the sweet spot. Just keep that in mind. So I don't have any problem with these AND gates because they have 4 inputs. They're good. But I have problem with this OR gate. So how can I get rid of this 8 fan-in? And by the way, if you see the actual data, hopefully in 433, you will feel how, ridiculously, challenging it is to design this really high fan-in gates. It's completely unusable, for example. So it looks okay in terms of circuit design, but practically it's not the best thing to do. So what we can do is we can make it multi-stage. And I hope by now you know how to make multi-stage. Now, if I ask you this question, this could be a true false as well, just to give you a sense. Between this functional expression and the other expression, which is basically a different version of the same functional expression. So what we have done here is we have taken a few terms common, that's all. See, so for example, here, A prime, B prime could be taken common between these two. And you have these two terms side by side. Can I do that? Will anything change? In terms of Boolean logic, nothing will change. But in terms of hardware implementation, can anybody tell me what will change here? Which one will have more stage? Option 1 or option 2? Without drawing the circuit, can you tell me? Based on your understanding? I did mention that. Please make sure to review. If you basically represent this in a complete sum of product format, that will always be the minimum stages, which is 2. And anything beyond that will have more stages. Okay. So is this a sum of product form? No, because it's a mixed format. The sum of product was this. Everything is, all of these are product terms, and then you have sum of products. So SOP. It's not statement of purpose, it's sum of product. All right. So versus this is not an SOP, this is not a POS, product of sum. This is something mixed in between. So anything that is a mixed of sum of product and product of sum will have more stages. Does that make sense? Will you have to? Now, that is the difference between doing well in quiz and doing well given more time. So I know the questions that will be set in quizzes or other midterms and whatnot, you can all answer them, honestly, given enough time. But how many of you will be able to answer quick enough? That is the question, because that's how real life is. You have to take quick decision. You get a few seconds, few minutes, depending on the criticality of the situation to decide, right? If I give you all the time in the world, anybody could figure out anything, honestly. So there will be some people who will try to implement that in circuits and see how many stages are there. And some of them will use this background knowledge. And this could also work. I don't know if you have tried interviewing for internships or full-time jobs yet. Especially the big companies, like if you do it for Nvidia, Google, Intel, like the big players, they will take interview and they will just jump into direct technical questions, and they will ask you questions very quickly. They will not give you time to settle down and check your notes or maybe like do anything. They want to see whether it's in the top of your mind or not. And you cannot memorize, your, interview, honestly. Like you cannot memorize stuffs for your interview, and that will make you nervous, first of all, and more importantly, that will show up because they will make sure that they ask you a question that is common sense. You cannot just memorize this, right? And after the interview is over, you'll see, oh man, that was so easy. I mean, come on. Or I mean, it feels even odd to see it that way. If it were a very difficult question, then okay, I don't care. I mean, I'm not even supposed to know this. But that's not the case. They typically ask you very simple, basic questions. All right. I'm sorry for taking the tangent, but I I hope it will. What I'm trying to stress here is make sure you have these concepts in the back of your head. That's why I'm trying to stress it over and over again. So by the time you finish this course, you should have common sense about digital logic, not necessarily remember all this process, like being able to do K-maps. Do you think within a phone interview, people can test your K-map skill? No. They'll not ask you to do a very complicated K-map because they cannot see you doing stuff. But they can ask you something that will test whether you really understand. All right. Anyways, now, I hope it's easier for us to now implement this in steps. So first you have to do a 2-input AND gate, which is C prime I0, which is this one. So you need C and C prime and I0. So that's an 2-input gate and another 2-input gate. And then you have to take an OR gate, and then you have to take an AND gate eventually. So gate, 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 gate. So basically 4 stages essentially here. And we have done that before in the previous lecture, so I'm not going through it. And there is one other step that I don't know if you have noticed it. This is taken from textbook as an example. This is the contrast between what plain vanilla implementation looks like if you don't have any other consideration, and this is what an optimized implementation may look like. Notice they have always used NAND gate. Do you see that? Did we discuss how to convert an AND or chain into a completely NAND-based design? Did we? Okay, we did. That's why that lecture came before this one, so that I could just fast forward, I hope. But it's up to you to check it out. Don't just take my word for it. Try to first implement it in form of AND and OR at home, AND and OR. And then try converting that, the OR gate and AND gates, to NAND gate using the exact same approach we learned in the previous lectures. And you never know, this could be set as your midterm question as well. Like, hey, I give you the AND OR version of this circuit and ask you to convert it. You see my point here? Okay, so please try this out. Don't just let them go. If you face any issues, you know where to find me. But if you don't try, you never face any issues actually. So, but you face the first issue during your exam, which is not the fun way to find out. All right. So moving to the next level, I will show you some, example use cases, of course, so that it makes sense for us to use multiplexers as a building block. And also, there is another new concept here, which is the concept of bus. Okay, and we'll talk about it in a second. So imagine you have two numbers, two 4-bit numbers, and the numbers could be represented in forms of like x0, x1, x2, x3. So 4 bits. So basically say 1, 0, 1, 0. So this is like x0, x1, x2, x3, something like that. So you have a 4-bit number and another 4-bit number. And you want to select one of these numbers, one of them, not both of them simultaneously, all right? So you have 1010 or 1111. You are choosing between either of them. So this is one way to do so. Basically, since you're choosing between two numbers, it's either A or B, say. You can connect every bit of that number, one of the numbers, as an input to a 2-input mux. And the corresponding bits of the second number as input to the same mux, as you see. So when you select, this is your select signal. This is a 2-input mux. That means you just need 1 bit of select signal, 1 bit. If you make it 0, it will always select X. If your select is 1, it will always select Y. So you can selectively load the number you want to use. You just control the select signal to say 0, and you have all the X components. Or you could convert it to 1 and you get all the Y components. Does that make sense? Did you ever try to select something from a drop-down menu? Like select this versus that? That's in software. But this is essentially a drop-down menu for hardware. Do you see that? So the action that you do, like select, is basically the select signal that you apply in hardware. Right? And you don't have to just choose between two numbers. What if you have 8 options? Choose between 8 options. Choose one of them. You need a 8 to 1 mux. So mux is basically the hardware analog of the drop-down menu in a software or like a user interface. Do you see that? And trust me, no software exists without matching hardware. You can imagine that. Like they don't just work in the actual cloud. You understand that cloud is a hardware, right? There is a funny story I can tell you. I went to a robot competition when I was an undergrad, like you, in a different country. It was an international one. And at that, it was like a long time ago, as you can imagine. Basically, we had a robot. We could upload the instruction on cloud rather than just accessing the robot like in person. And the robot used to download the instruction from cloud and behave accordingly. So all I have to do is update a file on the cloud. And you could just, obviously, it's so remote that as long as it's connected to the internet, it will work. It's a long time ago. At that time, people didn't really understand what cloud is. So I was trying to explain. So it takes instruction from the cloud. And everybody, like the audience was looking at the sky, like, okay, it's coming from the clouds. I'm not kidding, right? So seriously, so cloud was not that common at the time. Now we can all understand cloud means like Google Drive, OneDrive, you upload it on cloud. And at the time, they really thought that it's coming from the cloud. So just see how things change. So sorry, this is a tangent. But the point is, anything that a cloud that we think about, cloud is nothing but high performance computing system in a data center sitting somewhere. So there is a hardware. There is no software, even the cloud that, I mean, it's not a hardware, it's not a portable hard drive. You're uploading it, but eventually it is getting to a hardware. There is no software that exists without a hardware analog. So that's exactly what I'm trying to tell you. Mux or multiplexer is basically an analog of basically like a drop-down menu. Does that make sense, folks? First of all. Number 2, how can I, like imagine if I have a hardware diagram, especially, for example, you're trying to draw a diagram for a Core i7 processor. It will make the engineers crazy to keep tracking all those hardware components if you go down to that level of granularity. So we try to abstract it out in a higher level and reduce the number of symbols we want to use. And this concept of bus helps us. And you can read this that I've written here at home. But long story short, when you have a number of bits that basically represent the same thing, right? It's a repetitive circuit. You could represent that in form of a bus. So as if it's a data line that gives you 4 bits. They are doing exactly the same thing. It's a repeat copy of the same thing, but you do it 4 times, 8 times, 16 times. What you do is, instead of showing these 4 marks separately, you draw it this way. You show that you have an input X with 4 bits, and this symbol, you just cross it out. It represents a bus, data bus or something like that. If I write 32, it represents a 32-bit bus. So basically, if I don't do it this way, I'll have to draw this 32 times, which is like crazy, right? To the point. Same here. So you take X and Y and you select between the two, and X and Y both will have 4 bits. That means this essentially represents 4 individual mux circuits. And your output will also be 4-bit. You know how? For example, so from here, you get 1 bit, 2 bit, 3 bit, 4 bit. But you combine them into just one line and show that you have 4 bits of output. And these are particularly helpful if you see, like, just Google it. Say architecture diagram for Core i7. You'll see different lines, like wires going in and out, and beside the wire they will write 64, 64. It represents you have 64 lines like this, each having 1 bit. So it's a bus with 64 bits. Does that make sense? So do you understand the concept of bus now? If you see a logic diagram moving forward in one of the textbooks, will you recognize that this is essentially the copy of the same circuit 64 times? Okay, so moving to the next concept, buffers. I told you we are learning about the building blocks. It's like, okay, these are the Legos you have available. Will you make a car out of it, or will you make a house, or will you make whatever you want to make out of it? You have a certain number of building blocks. So these are at your disposal. If you want to use multiplexer for some reason, you can. If you want to use buffers, inverters, decoders, encoders, you can, depending on what the situation calls for. So what are buffers? In this circuit, I hope you recognize this is an OR gate. This is an AND gate. So we know all of this except for one. Can anybody tell me what this thing is? Using your common sense, you can tell I'm going to say it's a buffer, but it looks like an inverter. What is missing? Yes, thank you. So it doesn't have a bubble in front of it. So if there is a bubble, that is called an inverter. Okay, get used to this term. In some textbooks, they call it a NOT gate. So NOT gate and inverter is essentially the same thing. It basically inverts the input. That's all. What a buffer does, it doesn't change anything to the input. If your input is 0, your output is 0. Input is 1, output is 1. You might be wondering, how is that even useful? Come on, it's not doing anything. It's just giving me the same input again. So why will I even use this? It's a gate. It's a logic gate that doesn't change the input in any way. It deals with just one input, gives you one output, and it basically copies the input to the output. Can anybody guess why and how that might be useful? Of course, you can imagine it's mentioned here, but don't read it now. Use your common sense. Yes. Great point. Thank you. I will come to that. Yes. Okay, thank you. Both of you are correct and you are on point. Basically, one thing that you must have seen, that when you insert a logic gate, think of them like chunk of capacitors. Any logic gate, if there is nothing else, they will bring in capacitors. So by inserting buffers, which doesn't change anything, you are adding delay. So that's good. Buffer insertion, essentially, buffer insertion is a step in VLSI design, very large scale integration design, that people often use to balance out the branches. If there is one branch that is super fast and the other is slow, it doesn't help you actually. Simply because one of them was fast, that doesn't mean that the overall gate will work well, because it will give you all sorts of wrong output. So you slow it down. Yes. Yes, thank you. Thank you. You are right. So both of you are right. In fact, thank you for adding 2 extra points, which is not covered in this slide. So this slide will talk about a third application, but I'm glad that you brought up this too. Number 1, buffer insertion to balance out paths. Imagine you have 2 paths, path A and path B, and path A is way faster than path B. You don't like it because eventually the output will be all messed up. What you do is, to slow it down, you insert buffer. as many as you want. If you want, insert one buffer that introduces a 20 nanosecond, two buffers, 40 nanosecond, three buffers, 60 nanosecond. So you keep inserting buffers to slow it down. Okay. That, as you can see, it may not be the most ideal thing to do, but you might have to do it to make sure things at least work. Number two, regenerating signal. I haven't told, I teach this in 433. CMOS logic gates have regenerative property. What it means is when you try to provide a voltage through a chip which has millions of components. Imagine you apply 2 volt of signal in one of the nodes and you take it out to multiple directions. You run different components in the circuit with the same voltage, right? Do you think, according to the convention, we understand that all of these nodes will have the exact same voltage? At least that's how the simulator works, because they consider ideal interconnect. But practically, there will always be resistance in the wires. You see that? So because of this resistance, you'll never get full 2 volt in every node. Sometimes it will be 1.2, sometimes it will be 1.8, sometimes it will be 1.6, it will be all over the place. So it creates a challenge, a nightmare essentially, for the circuit designers. Okay, so if you design circuits for a certain supply voltage, say 2 volt, you design your circuit for 2 volt supply voltage, you expect to have 2 volt, but you get 1.8, 1.6, your circuits will just be messed up. I mean, like I said, the more I tell you this information, you feel like, how do things even work? I mean, they shouldn't even work at all, right? Okay, so one approach to make sure that we have the exact same voltage everywhere would be to use buffers every once in a while across different paths, because buffers, the beauty of CMOS logic gate, not just buffer, any logic gate, but buffers are good because they don't change anything. Other logic gates will change stuff as well, right? The moment you use buffer, this 1.8 volt will go back to 2 volt, like the full VDD. Any logic gate will take your voltage to full 0 and VDD. This is called rail to rail swing. Okay, this is known in VLSI design. Rail, basically rail means VDD and ground. So it takes you all the way to the ceiling or floor, depending on what you want. Okay, it's not like the VDD that gets contaminated. Sometimes ground changes too. Instead of 0, you get like a small voltage, 0.1, not fully 0. Okay, because of some other reasons. So you can also regenerate ground using the same approach. Okay, so these are additional points beyond what I wanted to discuss. So which is good, gives you additional information. But the point that is covered here is, imagine you are trying to drive multiple logic gates with the same gate here. Say this is an OR gate trying to drive multiple AND gates. What happens is, as you can imagine, the current will be distributed, and the current, say, imagine if you have 10 ampere current, I mean, this is obviously infeasible, say 10 microampere current coming in, it will be distributed across, all the branches. And the more branches you have, the less current you will eventually get. So they will become slower because it will take more time to charge up the capacitors at the input. Every input will have capacitors. It will take you more time. And we discussed this before. How can you change that? Remember, without doing anything to this logic gate, what you can do is you can use a buffer. And the good thing about buffer is they don't change the logic, but they can be sized up or down. Remember, the higher the size is, the larger the size of a logic gate is, the more current it provides. So imagine you design an OR gate, you use it everywhere. You don't change the size of every OR gate. You use it exactly as is. But you have different sizes of buffer. Sometimes we write it this way: 1, 2, 3. That means it's twice the size of a regular buffer, 3 times the size of a regular buffer, like bigger buffers. So the bigger the buffer is, more current it can provide. It's like a regeneration block that creates and provides more current. Okay, it doesn't change the voltage level, it doesn't change the logic, it just provides more current so that you can drive multiple outputs. So buffers are also used whenever you need to branch out and drive more loads. If you need to drive 8, you use a bigger buffer. If you need to drive 2, you use a smaller buffer. So you have different sizes of buffers. Instead of having different sizes of OR gate, you have different sizes of buffer with the OR gate to help drive outputs. Did I make sense at all? Okay, so this is also design philosophy, by the way. You could have asked me, hey, instead of using buffer, why don't I have different sizes of OR gate? Okay, I size up the OR gates over and over again. That's a design choice, remember. What engineers do, imagine if you join Intel, for example, or NVIDIA or AMD, they all have their standard cell library. And the engineers, imagine your job when you join is to make the perfect NAND gate or perfect OR gate possible. Like you, obviously, you don't just design it. Oh, there you go, OR gate. No, you go deeper into it. You see the actual transistors. You optimize the transistors. You optimize the interconnects. You optimize the contacts where the voltages come and current go through. So this is a very complicated approach. It looks okay when you look at the high level block diagram, but as you go deeper, it's a lot of work. So yes. Yes, that's a great question. Yes, oftentimes the algorithm remains the same, but the underlying design can differ, of course, and they have different strategies. For example, one of the common strategy is to make sure you have a set of standard logic cells. Like sometimes we say two NAND, that means two input NAND gate, two AND, that is two input AND gate. We typically don't play with the sizes of these AND gates because how many can you do? For example, imagine for a certain branch of your circuit or system, you need 8 branches. For another branch, you need 13. For another branch, you need 17. How many samples will you make? Right? Imagine you are the NAND engineer whose job is to make the NAND gate. And I ask you to make 50 different kinds of NAND gate. I mean, isn't that going to be challenging for you? Versus what you can do is you can make one NAND gate, which is perfect, fully optimized, lowest power, highest speed, like the best you can. It's a work of art. You have a NAND gate, you upload it to the standard cell library. Your colleagues work on XOR gate, OR gate, NAND, blah, blah, blah. You see my point. And not just a gate, there are many other components in the hardware design. And you haven't even learned about them yet. There are flip-flops, there are memories, there are many other things. So NAND gate is just one thing. There are hundreds of engineers who work in one group, and your job is to make the NAND gate. If something goes wrong with the NAND gate, they will come after you. Okay. So, and then after you make all of these components, just imagine if you had to make or change their size individually, you need like almost infinite number of components, like 50 NAND gates, 50 NOR gate, 50 XOR gate. Even then you don't cover everything. There will be situations where, oh, I don't have that flavor. I don't have that version, right? However, if you make a certain number of buffers, NOR gates, NAND gates remain the same. What you have is maybe you have 1, 2, 7, 5, 3, some different sizes of the buffer. You can combine them selectively because they don't change the logic. You can always connect 1 with 7 to make 8. You see my point here? You add 2 buffers, 1 and 7 to make 8. So that's how you can have any arbitrary sizes, any arbitrary branches using buffers. So that's why buffers are useful. They don't do anything in terms of logic, but they help you achieve any number of branching in a circuit without making your life difficult. Does that make sense to you in terms of how things work in actual? All right. So this simple benign circuit has a lot of purpose. Without it, no practical design can work. Okay, move to the next one. Tri-state buffer. It's a different kind of buffer. Its purpose is also to connect different nodes, one with the other, but it has an extra feature. It has a select signal like the multiplexer, like the mux. If you enable this by say providing 1, it then connects the input to the output. Otherwise, it disconnects the input from the output. That is the unique part about mux. I mean, I'm preempting a question here. I expect that you will have this question at some point. In a mux circuit, there is no way that no inputs will be connected to output. That's impossible. At least one of them will be connected to the output. Even when all the input select signals are 0, you'll connect the first one to the output, right? At least one of the inputs will always be connected to the output. There is no way you can completely disconnect the output. That, hey, there is no input. That is impossible in a mux circuit. Am I making sense, folks? You never disconnect the output from the input. Something will be connected. But in a tri-state buffer or 3-state buffer, that is the unique feature. it can allow you to completely disconnect, like basically taking out the switch, completely disconnect the input from the output. So that is the unique feature of this logic block. Are you all with me? So that introduces a new state which we haven't seen before. When something is not connected to anything, the output is literally, as I'm going to use the term here, it is literally floating. You don't say that the output is zero. No, zero is something that you impose. You drive something to zero or drive something to VDD. You don't disconnect and just assume that it's going to be zero or VDD because you don't have any control over the output now. You don't know what the output is going to be because you don't connect anything. So this is called a high impedance situation. This is it's also mentioned here. You can read it. In some textbooks, they call it high Z. Z represents impedance. So it's also known as high impedance condition, right? What it means is essentially when you disconnect two nodes, okay, if I cut a wire, right? What I have in between these two branches? Air. What is air? Insulator. What does insulator have? A very high resistance or very high impedance, I can say. So essentially, disconnection represents high impedance. That's exactly what it is. So what this logic gate does, it creates a really high impedance in between the output and input if you provide a certain select signal, 0 or 1, depending on how you design it. Otherwise, it basically provides a low impedance, really low resistance path, which makes, it basically connects the input to the output. So you either connect it or disconnect it. And you will encounter this situation that, hey, I don't want to make it 0. I don't want to make it VDD. I just want to disconnect it. And that's how you do it using tri-state buffer. Okay. Are you still with me? No? Have you given up already? Okay. All right. All right. Now, see, there are multiple symbols that you will encounter in your career moving forward. And remember, this is a building, this is a foundational course. We are preparing you for the next steps. When you get to the higher level courses, they will just assume you know this. You know what this thing is, right? They'll say, okay, hold on a second. What are these bubbles for? So don't be intimidated by this. It's very simple. First of all, this symbol represents, let me explain. B is your select signal. When B is 0, whatever your input is, whether it is 0 or 1, you don't care because your output is disconnected. When the output is disconnected, its state is not called 0 or 1. It is called Z because it's a high impedance situation. Does that make sense, folks? If I were you, I would have asked this. I had this exact same question when I was in your stage. Okay, how is that different from not having anything? If it is 0, then what's the big deal? Basically, what it does is when your input is not driving an output, say imagine your output was VDD in the previous cycle, it was VDD. It can randomly change by environmental aberration. Because of noise, it could go slightly up to VDD, plus delta V, or it could go down minus delta V. It could go up or down slightly. If it were, say, 0, instead of staying at 0 because of random fluctuations from the environment or interference, it could go up to, say, 0.1 volt or something like that. It could change. But if you drive this to 0, it will remain 0. This environmental noise will not change it at all. Does that make sense? That is the difference between driving and floating a node. A floating node can be easily, hampered or changed by environmental aberration, fluctuations, interference. But a node that is being driven cannot be changed that way. So you're basically letting the node, do whatever it wants. That's what floating node means. That's why high impedance is, what high impedance means. All right. Now, when my select signal is 1, notice this is the case where select signal is 1. You connect the input to the output. So what does that mean in terms of truth table? When you see 0 as input, your output is 0. When your input is 1, your output is 1. That's exactly what you see. Don't you? So notice, I told you every slide will introduce something new. It might feel boring and repetitive, but there will be something new. Have you ever seen this Z as logic input or output ever before? You have seen 0 and 1 and one more thing. What is that? Don't care. Did you see don't care? But this is not even don't care. It is basically a floating node, which is a unique concept that we are learning for the first time. That's why it is important. Yes. It's a great question. Well, all right. There are many circuits where, and I can give you the name of one. It's called SRAM, static random access memory. There is no electronic device in this room that doesn't have SRAM in it. So it's everywhere. You cannot name a single electronic device that doesn't have SRAM. Okay. So for SRAM, it's a memory. You have to store information in it. Okay. So when we read from SRAM, before we read, we charge up a node and let it float. Literally, and I'm using the term float. You make the node floating. You don't drive it. You don't make it zero. You don't make it VDD. You just let it do whatever it wants to do. And you basically see, have you seen someone measure your blood pressure? What do? They just pump up the pressure and then let it go like as it wills, right? They just wait and hear, right? That's basically what you do. You pump up the circuit. We call it pre-charge. We pre-charge the circuit to a level and let it float. And we see whether it goes up further or goes down further. Does that make sense? If it goes up by itself, we are just letting it float, do its thing. If it keeps going up, that means the information that was stored was Boolean 1. If it gradually goes down by itself, that means the information that was stored was Boolean 0. That's how you sense it, like exactly how we read blood pressure. You pump it and then you wait. Similar, we pump the circuit with voltage or charge versus, and then we just let it float. See, this is exactly a use case for a situation like this, a gate like this, where you just let it float. Does that make sense, folks? And if you make it 0, it's not going to go up because you're driving it to 0. If you let it connect it to VDD, it's going to stay at VDD. It's not going to change. So you don't sense. So to sense the stored data, how do I know what it's storing? That's how we read. You basically let it float. Yes. So yeah, exactly. So basically, Z represents that moment of time when we let it float. But after, like, we let it float for a while. We don't just let it be forever. Like, for example, for 2 nanoseconds, we let it float. And after that, we drive it again. When we try to drive it again, we could then sense using circuits called sense amplifier. There is a separate circuit that tests the voltage level. Is it above a certain level or below a certain level? That's the purpose of that circuit. It's called a sense amplifier circuit, right? It's an analog circuit. And then that circuit tells you, hey, when you let this guy float, it actually increased in voltage. So it was storing 1. Or when you let it float, it decreased in voltage. So it was storing 0. So that's, you need additional circuits for that, right? Did I answer your questions? All right. Okay. So, like I said, they will make sense as you move forward in hierarchy of courses. Okay. What is the difference here? Don't be, like I said, don't be intimidated by this. All it just does exactly as this buffer does, except it does the opposite. Meaning, it not only provides the input to the output, it also inverts it. Okay, so basically whenever A is 0, your C is 1, A is 1, C is 0. Exactly the same, but inverted. But, in terms of, the high impedance node, nothing changes. As long as B is 0, your node is always high impedance. Are you all with me so far? Okay. Now, how about this one? Basically, this inverts the select signal. For the first 2 examples, when B is 0, your outputs were floating. But for this particular buffer, for B is 0, it does its thing. When B is 1, it becomes floating. Does that make sense, folks? Okay, so exactly opposite select. I mean, who told you that you have to let it float when the input is 0? You decided. Now, your circuit might require that when an input signal becomes 1, your output becomes floating. It may be so. Am I making sense, folks? And then you use the other kind of buffer. So apparently you have 4 types. Why? Because you can mix and match them to make anything you want. So that's the hardware building blocks I told you. You have 4 kinds. And what is the 4th kind? It basically floats a node when the input is 1, like this. and also invert the input to the output. So it's basically same as this one, except the select signal is inverted. That's all. So you have 4 different types. And notice this is all the possibility. Okay. Just imagine like if you have different kinds of blocks and it's mirror image, for example, then you can make anything. But if you just have one kind, then it is difficult for you to make any random shape. I don't know if I'm making sense here. You need a type of shape and it's mirror image to make sure you can make everything. Okay, so they're essentially mirror imaging each other. All right, let's move to the next one. And hopefully this slide, I chose this slide particularly to show you why there are different kinds of tri-state buffers. This is hopefully going to show you. Imagine you are trying to make a circuit where, depending on a certain input, you either choose this input and connect to the output, or choose the other input and connect it to the output. Does that make sense? Do you see what I'm trying to do here? Okay, so your input signal is B. When B is 0, folks, look at this. Look at these two tri-state buffers. Which one will be in high impedance mode for 0? I know you haven't memorized it yet, but yes, but this one, because there is no circle on top of it, right? So for 0, this one will be in high impedance mode. So it's disconnected, but the other one will be active. So this will drive D. So D will be A when B is 0. So when B becomes 1, the other one will go to the output. Hey, hold on a second. Doesn't it look like a 2-input mux? What does a mux do? When B is 0, A goes to D. When B is 1, C goes to D. Don't you think? So basically what we have done is we have made a mux using 2 tri-state buffers. It's like building blocks, right? Mux is a different circuit, by the way. It's not like mux will always be made of this buffer. We can make mux. How did we make mux, folks? In the first few slides, we saw that using OR gate and AND gate. There was no buffer, yes, right? Remember that? But you can also make a mux out of buffer. And this is an easy example, very easy to explain example of why you need both kinds. By merging them two, you can achieve selective selection. Okay? Now, the second example will illustrate the confusion that may arise when you use the same type of buffers over like without mixing them up together. This is the last thing that we'll cover in today's class, right? Can you pay attention to this for like 2 minutes? It'll be okay, like after this. Let's see. So when you mix 2 tri-state buffers and you're trying to drive the output with them, both of them. Remember, high impedance node is always challenging, right? Notice when this is S1 and S2, what does this mean? S1 is this output, S2 is this output. Okay, so the possible output for S2 would be, you could either have 0 or 1, or it could be high impedance node. Do you guys all agree with it? Or here, this could also be 0 or 1, or it could be high impedance node. Don't worry about X for now. I'll explain that in a second, all right? So when S2 is 0, S1 is 0, which is this combination. Do you have any confusion about the state of the output? Both agree, so it's gonna be 0. When both are 1, which is this case, do you have any confusion about the state of the output F? Both agree, so they will both drive the output to 1. But what if one of the output is 0 and other one is 1? What then? I mean, they will fight. You don't know which one will win. And then you can have different sizes of buffer. This could be 2, this could be 4. And the bigger one will win or try to win, but the other one will keep fighting. So your output will be something in between VDD and 0. Does that make sense? So that's why the X comes. So we don't know. It's a confusing situation. Oh, by the way, before I end, what if your output S2 is Z, S1 is also Z? Both are floating, both are disconnected. Only then your function will be disconnected. So Z and Z will give you Z. Does that make sense? However, if one of them is floating, so this is floating, this is 1. So Z and 1, what will be your output? One of them floating, fine, but we don't care. We have another one driving the output. So your output is 1. Does that make sense, folks? Okay. Final, the last point. How about X and X? What does that mean? How do you get X and X here? Notice an output could be undefined. We don't know what the output is because of some confusion. It is also possible that you're driving these inputs with a node like this, which has a confusing output. You don't know the output of that input. So when you propagate that to the existing output, that also becomes confusing. So if your inputs are themselves confusing, when your inputs are themselves confusing, your output will definitely be confusing. That's exactly what it means. Okay. I know we are out of time. So think about it. We'll repeat it in the next class. All right. Thank you. Take care.